Welcome to the next lesson, Case Study Number 11, Search Engine Platform. Let's get started. Lamar is a librarian who loves technology and seeks to build a simple search engine to help users find specific resources in his library's digital archive. He aims to make locating relevant books, research papers, and other materials easier. He plans to build a strong back-end system for efficient search and retrieval to achieve this. Here are the requirements. The system must effectively search and organize metadata and text from the library's digital archive. The system's search results should be ranked from most relevant to least relevant, as can be found in most modern search engines. The system must manage increasingly large amounts of data while keeping performance fast as the archive expands. The system must maintain logs of search activities. The system must provide Lamar with the ability to expand the archive. Now let's get started with the design. Right. First and foremost, we have the user that we'll go ahead and put on this side. Now, here's the thing. And then let's go ahead and put a web service over here because that's where going to be the primary place where the user interfaces with the system. So web service where, they're able to go ahead and write queries to get relevant results. So let's put that right over here. Web service. All right. So now what I'm going to just first do, just for an idea here, is that we know that we want to have the ability to rank search results. So I'm just going to go off the back, have another box, and have something designated as the ranking service. Okay. All right. And then as we have this ranking service, we also, there's all this idea of the system must maintain logs of search activities. We're going to just maintain a log of some sort. So let's go, we're connected to the ranking server itself because every time something's ranked, we want to have a log of that for maybe future purposes. So let's put a service here with a file store because file stores make, good logs. It's, logs, they might be structured format, but they're usually in the form of files. So a file store is a good choice. And we're going to go ahead and call that the search logging service. Okay. All right. So over here, we'll go ahead and use the elbow connector. I'm just going to connect these things together. So we understand that, every time somebody logs, every time somebody, hold on one second. Somebody takes a search result, the ranking service will rank the results in, using data that we'll talk about in a little bit. And then whatever it decides, it will be logged by the search logging service. So we understand that we have that fourth requirement done. Okay, so now there's a few things to consider. So the system must effectively search and organize metadata and text. System search results should be ranked from most relevant to least relevant. That's what we're going to encapsulate in a ranking service. That's going to take a bunch of inputs and be able to rank results based on those inputs in the query that's being given from the web service, right? The system must manage increasingly large amounts of data while keeping performance fast as the archive expands, right? So these three things we want to kind of keep in mind. Now, before I even go into what goes in the ranking service, let's just think here that we want to keep, what's a way that we can enhance performance in a very relatively quick and simple way that is outside of the actual system itself. Well, like we've done before, caches are really good. In this area, if you remember the case study when we talked about the social media platform, we cached feeds for each of the users so that when a user has it, they have that feed. Well, in search engines, you have something that, you do have a search or a list of things that typically happen. You have searches that happen often, trending searches that happen, that a lot of people are searching at the same time. It can be a very significant savings if you're able to If you notice that something is being searched for all the time, that you put it in a cache so that the next person who searches it can see the cache result as opposed to having it processed again. So therefore, we've seen this before. We're just going to call a different name, but we're going to have a service connected to a key value store. All right. And then we're going to call that the high frequency search term cache. All right. So we have this here, and the user connects to that, which connects to the web server. So anytime there's like a high frequency search cache, then it's saved in there, and then therefore um, those results will be saved in and loaded there very quickly because it's in the cache. Okay. All right. So we have this. Now let's talk about ranking service. The truth is, there's so many ways to do this, right? It all depends on what are the things you want to be able to do, or what are the things you want, how accurate you want the search to be, what information you want it to consider, things of that nature. So it's really, when it comes to ranking service, you just think about what are the systems you want to feed into it so it can have a relevant service. You have to think though that like it has to do this in a relatively quickly amount of time, because typically if you have a search engine, it's an interactive kind of concept. Nobody really wants to like put in a search and wait, an hour before for results, right? So you have to keep that in mind, that there needs to be some good responsiveness in the things that you pick. So for this case, especially given, like given the requirements, we had three pieces of information that the ranking service can consider, just, for illustration of this service. So this platform. So first, we're going to have a service connected to a relational database. And we're going to call this the document metadata service. The idea with here is that we want to save, and we want to save this in a consistent way, information about the document. So you put an ID, you do know that what's the title, what's the description, what is it about, things, information that we just we know about the topic. It could even have certain like topics, or you can even add some semantic meanings, or like genres, what have you, something that you can something that you can, like, that if happens to be in a query, we can easily like get that information from this document meta service and know exactly which data is associated with that. So we have like a piece of information that's very straightforward, saying that, okay, I'm searching, something with that title. You can get the title from this document meta service. That's why it's backed by a relational database. Then we can have a service connected to a key value store. And this is going to be an interesting one. And I'm going to talk more about this. I'll have more about this in the appendix below. I'm going to call it inverted index service. And what an inverted index does is that what it does is that it has the keys to be the actual terms you want to search on, or keywords, and then the value is actually the document IDs. So the idea is that you can go in and have a search query. It has certain keywords. You can use this index service to find out that, what documents has these certain keywords featured. It gives you the IDs, and you can use those IDs to go to the document metadata service to find out exactly where that document is, what is it about, what's its title, what's its description, what's its website, and where it is in the archive for the full version. So you have this ability here. And then the last one that we're going to have here is a service connected to a vector database. And what we're going to call this is the vector sentiment service. And again, as I mentioned, with vector databases, they're like relational databases, but they're a bunch of matrices in high dimensional form. We're able to take the full text of the actual document, convert into numbers, convert into vectors, and then be able to take the query and do the same thing and be able to find out like, what documents semantically like look like or similar to the query that's being asked. This is how you can get meaning towards like your search results. They're saying that like, oh, how do you get the computer to understand really what you're trying to say and then find documents that meet that? This is their strong points. Notice, the relational database is strong on making sure you can query exact data. Vector databases are very good at finding things that are similar to each other. We use both of them in their strings into this ranking service so that we can rank them and have like an equation there that takes these three pieces of information and can really say like, oh, hey, here's the 5 results or 10 results in order that, based on this search query. So we connect all these things to connect to the ranking service. Okay, so give me 1 second. All right, I want to connect these to the ranking service. All right, so then every time there's a query, it goes connects all these things, and access to these things can be pretty quick. So that means, and then that enables the ranker to be able to give a response quickly. Now, the thing is with this is that we need to always make sure that these pre-processing things are up to date. So I'm gonna actually first put something over here. We have to have an actual digital archive, right? Which would be a file store. Um, so the actual digital archive itself, which will have the actual documents here, archive survey. But you see, if we just had like, oh, ranking service searches the digital archive services file store every time and find relevant results, it will be extremely slow at best, or it just wouldn't even work as at worst. So we need to be able to populate these 3 pre-processing data that gives us this semantic meaning or metadata a lot faster, or like finding things based on keywords a lot faster than it would to do a full search on this file store. So what we do here is that I'm going to introduce a time element here. With the workers, we have what we call crawlers, right? So I'm going to call it here a document crawling workers, which periodically go ahead and crawl. And this is definitely outside of the whole search concept, search platform. They periodically crawl. So let me put this here. The digital archive, and then in kind, populate these 3 processing items. So let me go ahead and let's bring these to front to make this easier. And then you go ahead and use this elbow connector. They also connect here, here, and here, and they're actually populating these 3 in terms. So this ranking service is using these 3 pre-processing units to rank, and then these document crawling workers are crawling the digital archives and be able to populate it with the information that we need for the ranking service. So all of a sudden now we got most of our requirements here. Like we have a system that can effectively search. The search results should be ranked, right? Should manage increasingly large amounts of data while keeping performance fast as the archive expands. Must maintain system logs of search activities, but then here the system must provide Lamar with the ability to expand the archive. So what that gives us is, so we don't have what's it called? An authentication service. What we'll do instead is that, like a lot of times, especially if you're in a library, is sometimes there's like a VPN, a virtual private network, or some area that only Lamar will be able to access because of where he is. I'm actually going to put a separate thing over here and say, we'll say Lamar right there. He would have access to, and only him would have access to what we'll call a digital archive submit service where he can submit a new document into that to be populated to digital archive service. So we'll have Lamar here, we'll paste it over here, and this would automatically go to the digital archive service to be able to be populated. And also we'll have it kick off. We'll have this also kick off a worker as well. Let me just find a way to make this look a lot better. All right, just give me 1 second to finish this. There we go. All right, and so it submits it, goes ahead and puts in the digital article servers. It kicks off a document crawling worker, so it's crawling immediately as well. And so now we have our submit queue to be able to expand the archive and to make sure that it's populated in a pre-processing section so that the ranking service can access it for new searches. And here we got our system. All right, so let's go to the takeaways. First key takeaway: searching large data sets can be costly in terms of time and resources. It is beneficial to use methods that reduce the need for extensive searches. One way to do this is by using a service connected to a key value store to store frequently used query results. We call this the high-frequency search term cache. Here we can cache the results of searches that occur often and provide those results faster without taxing the rest of the system. The second key takeaway is the use of pre-processing information to make relevance and ranking more accurate. The 3 ones we have are the document metadata service, use relational database to retrieve standardized info on the matched document requested. The inverted index service, use key value store to provide a list of document IDs that match a particular keyword or search term. And lastly, the vector sentiment service, use vector databases to make semantic queries. Third key takeaway: you must pre-process data in order to use pre-processing data. The system allows Lamar to submit additions to the digital archive. Once resources are forwarded to the digital archive service by the digital archive submit service, document crawling workers periodically crawl new documents. The documents populate the 3 pre-processing services: the document metadata service, the inverted index service, and the vector sentiment service. Thank you so much. See you at the next one.